All right, section 4.6. This is our optimization word problems. Okay, so we have some steps to perform. I will try and perform all of these every time. This handout has 5 examples, and so we will work through all 5. All right, so first and foremost, make sure you read and understand the problem. Okay, draw a picture. Identify the given and required quantities. Right, assign a variable name to what is to be optimized. Make sure you identify it. What are we optimizing? Is it the length? Is it the area? Do we want maximum area or minimum area? Is it the volume? Do we want max volume or min volume? Is it a cost function that we're trying to optimize here? So make sure you know what you're trying to optimize, right? Find a governing function for it. So if it's area, length times width, or we have a cylinder coming, pi r squared h, okay? So we're going to find a governing function for it, right? Number 5 is the main difference between optimization problems and the related rate problems we did. When we're doing optimization, we are only allowed one variable every time. Okay, only one thing is allowed to be changing. Everything else is going to be changing with respect to that one variable. Right? So we're not going to take the derivative of a governing function that has more than one variable in it. We're always going to limit that to one variable. Right? Then we're going to do something extra. Okay, we're going to use the first derivative test to test whether we have a maximum or a minimum value. Actually, I think this should be the second derivative test. All right? So the second derivative test says if the second derivative is greater than 0, if it's positive, then we know our function is concave up. Well, guess what? If our function is concave up, then where the derivative is 0 is a minimum, right? Then where the derivative is 0 is a minimum. If the second derivative is less than 0, then we know our function's concave down. And so if this is what our function looks like, and when we set the derivative equal to 0, we know that that value is going to be a max. Okay, so we're going to kind of compare what the concavity is at those critical numbers of the first derivative. So we'll always make sure we do that, because we'd hate to find a minimum value when we really wanted a maximum value. Okay, so example number 1. A rancher has 100 feet of fencing to build a rectangular corral next to the barn. Okay, what are the dimensions of the corral to maximize the area? All right, so we're going to build a corral in the shape of a rectangle, and we're going to put it next to the barn. Now this is significant because the barn is going to be one side of this corral. All right, so I'm going to draw a picture here. Here's the barn, right, and here is my corral. So the fence really is just 3 sides, right? Here's my little fence, okay, with the wires sticking up, right? We're not going to fence next to the barn, okay, not necessary. All right, so this barn is going to have dimensions, let's use x and y, okay? So we're going to have x distance here, y distance here, and x distance here, right? So what do we know? We have 100 feet of fencing to build the rectangular corral. So all this fencing here has to add up to 100, right? So basically, we know that 2x plus y equals 100, right? And then what else do we know? Not much, right? But what are we trying to optimize, okay? What do we want? Do we want to maximize or minimize, and what, okay? So what are the dimensions of the corral, okay, x and y, to maximize the area? So we want to maximize the area. So we need a governing function for the area of this corral. Okay, so this is just a rectangle. Length times width is where it's at. So we get the area is equal to x times y, right? This is what we want to maximize, okay? We're going to maximize this. Now, before we maximize this, we need to get this in terms of one variable only, okay? Right now, we have x and y, two variables, okay? The a doesn't count. So we want to get rid of one of these. So how do we do that? Right? You're going to look at your given information. Were we given another equation somewhere that would allow us to substitute for x or y? Yes, we were, right? So if we take this amount of fencing, okay, it's easiest, it looks like, to solve for y. So if I solve for y, I get y is 100 minus 2x. Right? So I'm going to make the substitution for y here. Right? It really doesn't matter which variable we keep, but I just want to take the path of least resistance. Right? Y was the easiest one to solve for. So now I have area is equal to x times 100 minus 2x. Okay? This is my equation that I want to optimize. I'm going to go ahead and distribute the x. I get 100x minus 2x squared. Okay, here's my equation. So I know what I need to optimize. I came up with the formula. It's in terms of one variable. So now what I'm going to do is I'm going to differentiate this. Because where does the max or the min occur? It occurs where the derivative equals 0. All right, so I'm going to differentiate this function. Now on the a side, I'm just going to write a prime. And we're going to differentiate this with respect to x. So the derivative here is going to be 100 minus 4x. Okay. So in order to find the max or the min, I want to know where the derivative is 0. So I'm going to set the derivative equal to 0 and solve. So add 4x to both sides. Divide by 4. And I get x equals 25. Okay, so how do I know that that's a maximum and not a minimum? Right? How we're going to tell is we're going to do the second derivative, and we're going to figure out whether this graph is concave up or concave down. Okay, so let's do the second derivative test. So if I were to take the second derivative, right, I want to find a double prime. So the derivative of the derivative. So if I were to take the derivative here, I get the second derivative is really negative 4. Right? It doesn't matter what x is. The second derivative is always negative 4. So if the second derivative is negative, that means this graph is always concave down. Right? So therefore, our function, okay, a, is concave down, right? And if our graph is concave down, always, then the point where our derivative is 0 is a max, okay? Therefore, x equals 25 is a max. Right? This is what your second derivative test is going to look like, all right? So in equations where we're going to get two numbers here, one of them is probably going to be a max and one's going to be a min, and the second derivative test is going to help tell us that. All right, so I have x equals 25. All right, so I have an answer, but did I answer the question? All right, the question was, what are the dimensions of the corral to maximize the area? All right, so the dimensions are... Okay, obviously x is 25, so we have 25 here. What do we have here? Right? 25 feet by what? Remember, we have 100 feet of fencing, right? So we're going to put 25 feet here, 25 feet here. So we have 50 feet here, so we have 50 feet left for this horizontal distance. Okay, so our dimensions are 25 feet by 50 feet. That will maximize the area of this corral. All right? Next. Example 2. A box without a lid is to be made from a 12-inch by 12-inch piece of cardboard by cutting out a square from each corner and folding the sides up. Right? Find the largest volume that said box would have. What are the dimensions of the squares to be cut? So we've shown an example of this once before when we did related rates. But for now, okay, let's draw a flat representation of this box. All right. So we're going to start off with 12 inches by 12 inches. And we're going to cut a square out from each corner. All right. So I'm going to cut a square out by showing a set of dotted lines here. Okay, this is gone. This is gone. This is gone. And this is gone. All right, let me go see if I can get my box. All right, I don't know if you remember this piece of paper here or not, but this is my box simulation paper, right? So we start off with a square piece of cardboard or paper, and we cut out a square. So if I take these pieces off, right, this is what the cardboard looks like before we form the box. So in order to form the box, we're just going to fold each of these sides up, right? Okay, it's kind of hard to do on the camera, but we're going to fold each of these sides up, and we got ourselves a box without a top, right? So flattened out, it's just going to look like this. We have the base and the four sides there. Okay. So here we go. When we get our box, right, we're going to fold this up. So our box, here's the base of the box, right? So here's the base, and here's the sides, right? Side 1, side 2, side 3, side 4. And so we want to find the volume of this box. That means we need to know the length, the width, and the height, right? So I'm just going to call this the length, and this is the width, right? And then the height of our box, when we fold these up, this is our height, right? This is our height. Here. The height of our box is going to be whatever this dimension is, right? Now it's important so all of our sides are equal height, that every single one of these dotted lines is the same distance. So I'm going to call the height x, right? This is where I'm going to put the x. So I have x, 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 all right? So what we're trying to optimize, we're trying to find the largest volume, okay? So we want to maximize the volume. And so the volume has an equation, length times width times height, right? And this has 3 variables. We only want 1. So it is possible to write everything in terms of x, okay? The length here of this inner base here is going to be 12 inches, and then we're going to take an x distance off of each side. So the length is going to be 12 minus 2x. Right? The width, same thing. We started off with 12 inches, and we're going to cut x distance off of both sides, leaving the middle. So the width is 12 minus 2x. And the height, when we fold this flap up, the height is simply just x. All right, so here's our volume equation with just one variable. All right, so we do need to multiply this out so that we can differentiate it, or we could just do the derivative rule with 3 functions. Either way, all right. I do think I'm going to multiply this out though. All right, let's get v equals, multiply these 2 together. 144. 24 and 24 is 48. plus 4x squared. Okay, and then I'm going to multiply all that times x. So I'm going to get volume is 144x minus 48x squared plus 4x cubed. All right, here is my volume equation, ready to be optimized. Okay, we want to maximize this. So I need to take the derivative, okay, because the maximum is going to occur when the derivative equals 0. So what is the derivative of the volume here? We're going to get 144 minus 96x plus 12x squared, right? So I want to set this equal to 0. Okay. And I do think all three of those numbers, we can factor out a 12. So 144 divided by 12. I did know that, I promise. Okay, 96 divided by 12 was 8. And then 12 divided by 12. Okay. So I'm just dividing everything by 12, right? So then here, if I set this equal to 0, x squared minus 8x plus 12 equals 0, I need to factor that, right? So multiply to 12, add to negative 8. How about negative 2 and negative 6, right? Minus 2x minus 6x is negative 8. Negative 2 times negative 6 is positive 12. All right, so then I'm going to set each factor equal to 0, and I get two critical numbers. X equals 2 and x equals 6. One of them is going to be a maximum, one of them is going to be a minimum. All right, so I would like to do the second derivative test again. All right, so I'm going to box this off. Second derivative test. So what is the second derivative? Right? If I were to differentiate the derivative, I'm going to get negative 96 plus 24x. Right? So I want to know which one of these is a max and which one of these is a min. Okay, so I'm going to evaluate the second derivative at 2. Right, and so if I plug 2 into the second derivative, I get negative 96 plus 24 times 2. Right, negative 96 plus 48 is negative 48. Right, so that means the second derivative is negative. Okay, and if the second derivative is negative, that means the graph is concave down. And if the graph is concave down, that means that the value where the derivative is 0 is a max. Okay, so therefore 2 is a max. Right? Do I need to zoom that in? I'm kind of writing small. All right, so if I were to evaluate the second derivative at our other critical number, if I were to plug 6 into the second derivative, I would get negative 96 plus 24 times 6, which is obviously positive. All right, let's go ahead and do that. 24 times 6 minus 96 is positive 48. So the second derivative is positive. And if the second derivative is positive, our graph is concave up. Right? And if our graph is concave up, then where the derivative is 0 is a min. All right, so therefore 6 is a min. All right, so which answer did we want? Did we want to maximize the volume or minimize the volume? Okay, obviously we wanted to maximize the volume. All right, so we're going to pick 2 as our solution. All right, this is the one that maximizes. This is the one that minimizes. All right, so we have an answer. Okay, but let's make sure we answer the question. And the question is, find the largest volume that said box would have. Okay, so what is the volume? What length times width times height, right? So if x is 2, then we have the length is 12 minus 4, which is 8. and then the width is going to be 8 as well, and then the height is 2. So we get 64 times 2, which is 128. What are our units here? Inches cubed. Okay, so there's our volume. What are the dimensions of the squares to be cut? And we want the squares to be 2 inches by 2 inches. That will maximize our volume. So what's interesting here is, why is 6 a minimum? Okay, what happens when x equals 6? Right? What happens when we cut 6 inches from this side and 6 inches from this side? Right? We only have 12 inches to work with, so we basically have a box with 0 volume. Okay? So obviously this isn't going to be the solution. We want the squares to be 2 inches. All right? Moving on. Example 3. A cylindrical can is to be made to hold 1 liter. Right? Liter is metric, not metric. Liter is our a way of calculating volume, right? But what's better is to call liter 1,000 cubic centimeters, because centimeters can be both linear and multi-dimensional, right? So remember that 1 liter is 1,000 cubic centimeters. You probably already know that from your science classes. All right, my 4th grader knows this. All right, find the dimensions that will minimize the cost of the metal to manufacture the can. All right, so let's draw our cylindrical can. And we want to minimize the cost. All right, so the cost to manufacture this can is really multi-dimensional, but we're going to assume that the material costs the same, the side material, the top and the bottom material. Maybe, like welding this can together, we're not going to take that into play. We're just going to talk about the actual material, okay, the material to manufacture this can, right? So the cost comes from basically the surface area of this can, all right? Because we weren't given any information about welding or soldering it or taping it or whatever it is, all right? So we want to minimize, therefore, the surface area. Going along the assumption that the smaller the surface area, the smaller the cost, right? But we can't just make a super teeny tiny cylindrical can, because we have to hold 1 liter, right? So how do we get the surface area of this can, right? So this can has dimensions, right? It has radius and it has height. I think that's probably all we need, right? But the surface area of this can is going to be the top, right, as a circle, the bottom as a circle, and then the sides, right? If you slit this down the side, okay, if I were to kind of take a piece of paper here and pretend I have a can, okay, let me zoom out. Here's my can, right, with the sides. If I were to cut it down the side and fold it out, right, I end up with a rectangle, okay? So the sides of the can are going to be a rectangle. Here's the sides, or the side, all right? So in order to find the surface area, we need to add up the areas here. So the area of the top is pi r squared. The area of the bottom is pi r squared. Okay, what's the area of the sides? we have the height here, but what is this? Right? So again, here's your can, right? So if you cut the can, okay, and you cut it here, then the top is this distance, which is just the circumference of that circle, right? So the circumference is 2 pi r, so we get 2 pi r here and then h here. So the area of the sides is the area of this rectangle, 2 pi r h, right? So now I have a surface area formula. This is what I want to optimize. Okay, surface area is pi r squared plus pi r squared, which is 2 pi r squared plus 2 pi r h, right? Now before we can optimize this, we need to limit our variables to only one, right? And right now we have two variables. We have r and we have h. So there has to be an equation given in this problem that helps us eliminate one of those variables. And that is the fact that this can holds 1 liter, right? So the volume of this can is 1 liter. Right? So what's the volume of a cylinder? The area of the base times the height. Okay? So I know that the area of the base times the height is 1 liter, but I'm going to use 1,000 cubic centimeters. Okay? So what I can do here is I can either solve this equation for r or I could solve it for h. And I think solving it for h is easier. Right? So I'm just going to divide both sides by pi r squared. Right? So now I have h equals 1,000 divided by pi r squared. Okay, now this height is one-dimensional, so the dimensions here are just centimeters. Okay, which is why it's nice not to use liters, because what happens if you put liters in one dimension? I have no idea. All right, so let's not do that. Let's go ahead and substitute h equals 1,000 over pi r squared here. So now I have the surface area is 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Right. So the pi's will cancel. Right. The 1r will cancel. And so I'm left with 2,000 over r. Now, because we want to differentiate this, I'm going to go ahead and write this r. Instead of leaving it in the denominator, I'm going to bring it up and write it to the negative 1 power. So I get 2 pi r squared plus 2,000 r to the negative 1. Okay. So here's my surface area. Our cost comes from the surface area, and this is what we're trying to minimize, all right? I want to find the minimum value here. So I want to find where it's concave up, right? Not where it's concave down. So now that I have the surface area in terms of one variable, I'm ready to differentiate. So the derivative of surface area here, we're differentiating with terms of the variable, and the variables are, right? So we're going to get 4 pi r minus 2,000 r to the negative 2. Right? So I'm going to set that equal to 0. 4 pi r. Now I'm going to go ahead and move this back down because it's a little bit easier to solve for. Okay. Let's get rid of this fraction here. So let's multiply by r squared everything. Okay, to get rid of that fraction, so I get 0 equals 4 pi r cubed minus 2,000. Right? So solving for r now, add 2,000. Okay, divide by 4 pi. and then take the cube root, right? Cube root. All right, 2,000 divided by 4 pi cube rooted. Let's go ahead and figure out what that decimal is here. 2,000 divided by 4 pi is 159.15, right? If you didn't get 159.15, that's because you didn't put 4 pi in parentheses. All right, but we need to cube root this, so I'm going to raise this to the 1/3 power, and I'm going to get 5.4, right? So I'm just going to round it at the tenths place there, 5.4 centimeters. Right. Now we do have one other critical number for this derivative, and that's because we have an r in the denominator. 0 is going to be a critical number, but having a 0 radius makes no sense with this problem, so I'm just going to kind of ignore it, because if we have a 0 radius, we don't have a can, right? So I'm just going to treat the one critical number as our only viable solution here. But I do want to go ahead and take the second derivative and make sure that this graph is doing what it should be doing, okay? So the second derivative of the surface area, we're going to get 4 pi, and then negative 2 times negative 2,000 is plus 4,000 r to the negative 3. Okay. So if I were to change this, I get 4,000 plus 4,000 over r cubed. Now here's the thing, the radius is positive. I have a positive plus a positive. Right? The second derivative is always positive, right? Especially when our radius is positive. If our radius was negative, maybe we'll have a different story. But if I plug 5.4 in there, I get a positive number and a positive number. So the second derivative is positive. And so that means our function is concave up. And if our function is concave up, that means that 5.4 is indeed a minimum. Right, which is good because we wanted to minimize the cost. All right, so we have an answer. Okay, 5.4 centimeters. We verified that it is indeed a minimum. All right, but let's answer the question. Find the dimensions that will minimize the cost. All right, so the dimensions here, we just need to tell them what the radius should be and what the height should be. All right. So the radius is 5.4 centimeters. What should the height be? Right. Let's go ahead and just plug 5.4 into our height equation there. So 1,000 divided by parentheses pi times 5.4 squared is going to give us a height of 10.9 centimeters. Right? So it's pretty if the radius is 5.4, the diameter is 10.9, so it's kind of cubic, right? It's going to be just as wide as it is tall. That is going to minimize the cost of the metal to make the can, right? So why don't we see more cubic-like cans? Okay, that's because they reinforce the base. They use different materials for the base than they do the sides. Okay, they, how many seams it has adds to the cost. So this is a really simplistic version of actual cost of minimizing cans. All right, last two. Here we go. Example 4. Okay. Oops. I left the word in there. I know you see it. All right. The volume of a box without a lid is to be 1,000 cubic units. All right. What are the dimensions of the box that minimize the amount of material used? Okay. So we're not trying to find maximum volume here. We're trying to minimize the amount of material. Okay. So again, that's our surface area. Now, I think there's missing information here. In order to accurately do this, let's assume that the base is square. Because if we don't make that assumption, we're going to have too many variables. Right? Assume the base is a square. So I am going to draw a cube here, okay, with a square base or a box, right? Now this box has a square base, okay, so here's my base here. And so we're going to do the base and the 4 sides, and we want to minimize that. We have no top here. All right. So if the base is a square, I'm just going to let this be x, and then the height I'm going to let be h. Okay, not necessarily x. All right. So what are we trying to optimize? Okay, we want to minimize the material, i.e. the surface area. So we need to find the surface area of this box, right? So the surface area, okay, only 5 sides, right? The base and the 4 sides. So we're going to get the base, which is square, and then the 4 sides, right? Side, 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 side. Okay. So the dimension of the base, okay, x by x. What's the dimension of the side? Okay, this side is x times h. X on the bottom, h up the side. But it's going to be the same all the way around, right? X by h, x by h, x by h, right? So we have a surface area equal to x squared plus 4xh, right? The area of the base plus 4 times the area of the sides. Now before we can optimize this, we need to write this in terms of one variable. Right? We either need to get rid of the x or get rid of the h, whichever one's easier. There has to be another equation, okay? I didn't write it down yet. The other number we were given is this 1,000 cubic units, right? This is the volume, okay? So I know the volume is 1,000 units cubed, right? So what is the volume of this cube here, or this box? Length times width times height, right? So x squared h is equal to 1,000. Here's our other equation, okay, our other given information that is going to help us get rid of a variable here. So you can either solve this for x or you can solve it for h, but I suggest you solve it for h because that's easier, right? So I get h equals 1,000 divided by x squared, right? So I'm going to plug that in here. All right, so I'm going to get surface area is now x squared plus 4x times 1,000 over x squared, okay? Which again, I'm going to go ahead and let the x cancel. So I get 4,000 over x, and when I rewrite that, I'm going to change that x in the denominator to x to the negative 1 power because it's easier to differentiate. So surface area is x squared plus 4,000 x to the negative 1, right? Because this x is going to come up. So here's my surface area in terms of one variable. Okay. So to optimize this, we're going to find the derivative and set the derivative equal to 0. So the derivative of surface area is 2x minus 4,000 x to the negative 2. So when I set this equal to 0, I'm going to change that negative x to positive by moving it down, okay? And then I'm going to get rid of that fraction by multiplying everything by x squared, okay? So I get an equation 0 equals 2x cubed minus 4,000. So solving this for x, we're going to add 4,000 to both sides. We're going to divide by 2, and then we're going to take the cube root. Right. So I'm going to get a critical number, cube root of 2,000. Which is 12.6. Okay, I'm just going to round that. All right, so I get x equals 12.6. All right. Now, that's not our only critical number, again, because surface area has a negative exponent here, which means 0 is also a critical number, but 0 doesn't make sense with our problem, because if x was 0, we would have no box. All right, so let's go ahead and do our second derivative verification, our second derivative test. I want to make sure that this is a minimum and not a maximum, right? Because we want to minimize the material. So I'm going to take the second derivative. So the second derivative of surface area is 2 plus 8,000 x to the negative 3. Right? So just like the last time, if I go ahead and change that negative exponent to the denominator, okay, I'm plugging in a positive x in there. So a positive number plus a positive number is positive. So this is positive. If the second derivative is positive, we know that the function is concave up. And if the function is concave up, okay, then we know where the derivative is 0 has to be a minimum, right? So therefore, 12.6 is a minimum, all right? So we have an answer. Did we answer the question? Okay, the question asks for the dimensions of the box. All right, dimensions. Length times width times height. All right, 12.6 by 12.6 by, what's the height? Okay, let's go ahead and plug 12.6 in here. So 1,000 divided by 12.6 squared is 6.3. Okay, so here's our dimensions of the box. Okay, here's our final answer. Right, make sure you're doing this extra second derivative test when you calculate your solutions. All right, last example. A rectangle is bounded by the x-axis and the semicircle y equals rad 25 minus x squared. What is the length and width should the rectangle have so its area is a maximum? All right, camera, stop being yellow. We're just going to have to deal with the yellow video. All right, so we're going to draw a rectangle inside a semicircle. Right? So y equals the square root of 25 minus x squared is the top half of a circle. Right? And if you don't believe me, graph it. Okay? But this circle is going to be radius 5. Right? So I'm going to go 5, 5, 5. Right? And I'm going to draw the best semicircle I can muster. All right, here's my semicircle. It's kind of lopsided, sorry. All right, now we want to draw a rectangle in there. Okay, it's bounded by the x-axis, so it's not going to go below here. Okay, this rectangle is going to stay here, and so I'm just going to draw a random rectangle here. Okay. And what we want to do is we want to maximize the area. Okay, maximize area of the rectangle. All right, So the area of a rectangle, length times width, right? So this, let's call this the length, and let's call this the width, just so we know what we're referring to. All right, so what is the length of this rectangle? Okay, keep in mind, I could have drawn a really tall, skinny rectangle. Okay, I could have drawn a really flat rectangle. I kind of chose something in the middle, right? So the length of this rectangle is kind of dictated by this horizontal distance here, right? And this horizontal distance is basically so many units to the right and so many units to the left, right? Now, on the semicircle, okay, if we have a point at 3, 4, we're going to have a point at negative 3, 4, right? It's going to be symmetrical here. So this distance here is x, right? Because this is a point on the semicircle x, y, correct? Right? So this point is x units over and y units up. Everybody okay with that? This point here is x units over and y units up. So what is the length? The length is really 2x's. And what's the width? Just 1y. Okay? So the length is 2x and the width is y. Right? So here I have the area equation 2xy. So before I can optimize this, I need to get rid of either the x or the y. I need another equation that we can use to eliminate one of these variables, right? That other equation is right here, right? All the points are on, the points of, these 2 points are on that semicircle. So I know y equals the square root of 25 minus x squared. So I'm going to make that substitution here. Area is 2x times the square root of 25 minus x squared. Right? So now I have my area in terms of one variable only. Right? So I want to differentiate this. So in order to differentiate this, we have a product. Right? We have 2x times the square root. So we're going to do the derivative of the first times the second plus the derivative of the second times the first. So I'm going to go ahead and outline the product rule here. The derivative of the first times the second plus the derivative of the second times the first. Right? And so when we take the derivative of the first, easy peasy. Okay, the derivative of the second here, this is a chain rule. So I'm going to go ahead and outline the chain rule here, right? The outside function is the square root of x, and the inside function is 25 minus x squared, right? The derivative of the outside, the derivative of rad x is 1 over 2 rad x. The derivative of the inside is negative 2x, right? So to do the chain rule, we're going to plug b and a prime multiply times b prime. All right, so I get the derivative here. I really hate the fact that this kind of burnt out and is yellow. Sorry, guys. All right, my calculator kind of burnt that bulb out. All right, so the derivative of the first times the second plus the derivative of the second times the negative 2x. So this is b and a prime times b prime. That still needs to be multiplied times 2x. All right. So I get a derivative here that I want to set equal to 0. Okay, so I'm going to get 2 square roots of 25 minus x squared minus 4x squared. Actually, I should cancel a 2. Minus 2x squared over the square root of 25 minus x squared. Right. Whew, that was fun. So here we go. Let's go ahead and get rid of this fraction. So I'm going to multiply by the square root. just to cancel it, okay, get rid of it. It does add to our critical numbers. We want to make sure this doesn't equal 0, which is 5, okay? So we will kind of calculate that critical number as well, but let's go ahead and cancel this. So I get 0 equals. So if I multiply these square roots together, I'm going to get 2 times 25 minus x squared without a root. And then what's going to happen here is I'm just left with minus 2x squared. Okay. So I get 50 minus 2x squared minus 2x squared. So this is, minus 4x squared. So I'm going to add that over. 4x squared equals 50. Divide by 4. What, 25 halves? Okay. Take the square root, right? And the square root of 25 halves is going to be our critical number, right? So square root of 25 halves gets us a critical number, 3.54. Right. Now, keep in mind that we have a second critical number, right, where the derivative does not exist. Okay, so what is going to make this derivative not exist? If I'm dividing by 0, right? And so what number do I need to put in for x to make that equal to 0? That number is 5. Okay, we also can't put any number bigger than 5, right? Because then we have a negative under here. So we have an implied domain, basically -5 to 5, which is the edges of this semicircle. We don't want to go past -5. We don't want to go past 5 because then it won't be inscribed here. All right. So I'm going to go ahead and pick 5. Right. But what happens? Okay, if the x distance is 5, then the point on the unit circle is right here on the y-axis. I'm sorry, on the x-axis. So there is no height, right? So if I pick an x value that's 5 units away, I am at the, x-axis here, and I don't have any height to this rectangle, right? So this is going to be a minimum, okay? But let's make sure that this is a max. So I'm going to take, you know what? I'm not going to take the second derivative because I'm going to assume this is the minimum, and this is the maximum. All right. I could pull out maple, but guys, I just don't want to take the derivative of this again. Okay. So sue me. All right. Take me out to the streets and stone me. All right. But it's late again, and this is my last video, and I'm tired. But so I'm going to assume this is the maximum. Okay, this is the value that's going to maximize my area. So I have an answer. Did I answer the question? The question is, what's the length and the width? All right. So the length and the width. I have no idea where this cursive is coming from. All right. What's the length of our rectangle? All right. The length is 2 x's. Right. So the length is going to be 3.54 times 2, which is 7.08. And what's the width? Well, if I plug in, the width is y, right? So I just want to plug in 3.54 here, okay? And so the square root of 25 minus 3.54 squared gets me 3.54. All right, so the length is basically twice the width, all right? And that's going to maximize the area of our rectangle, right? Sans the second derivative test, please forgive me, okay? But there you have 4.6 optimization, right? Have a good night.